Okay. So module 7, organic chem, as most of you have already been through now, and many of you have exams coming on this module. There's a lot in this module, as I'm sure you've seen. It's a really content-heavy module, so different to 5 and 6 in the sense that 5 and 6 more conceptual, as we said yesterday, with some calculations in 5, more calculations in 6. Module 7, there's a lot more content, a lot more explaining to do, but it's a module that builds upon certain pillars. And once you lay a foundation at the start, everything builds almost identically across different functional groups. So the way that I've always taught people to approach Mod 7, it's a bit late to lay this out now, but just to say it anyway, is to start with nomenclature and structure to understand how everything's named, what the structures of things are. That will feed into explaining your properties, which can be either physical or chemical. So your physical properties, you're talking all about your boiling point, melting point, solubility, things like that. Or it can be chemical. And then, as we said yesterday, I said with the year 11s, a chemical reaction is anything where you have a change in composition. A physical change, you have no change in composition. So water boiling or melting is a physical change. Chemical change is any of the reactions you've seen. So hydration, dehydration, oxidation, they're all chemical reactions. So then from this, you would look at all your chemical pathways, and using both the physical and chemical applications, you would get your real life applications. So this sort of flowchart is how you want to think about each functional group. You're learning the nomenclature, the structure, building the properties on top of that, which are both physical and chemical, and that teaches you about the applications in real life. You're building this vertical pillar for every single one, and that's the way you should approach this module. So we'll crash through the nomenclature because most of you should have done this by now. In terms of nomenclature, we have to be able to name alkanes, alkenes, alkynes, alcohols, tell their primary, secondary, tertiary, name aldehydes and ketones, carboxylic acids, amines, and amides, as well as halogenated organic compounds and esters, which aren't on this list. And also I'll mention cycloalkanes as well. So we'll run through them very, very quickly. But before we do each individual function group, let's talk about a framework to get through the naming of any molecule. So whenever we're naming molecule, for example, this massive one, 3-methyl, 3-propyl, hexane, 2-ol, there are a few steps that we always follow for every single molecule we name. The first thing we always do is find the longest carbon chain, but there's a caveat. It has to be the longest carbon chain that contains the functional group if there is one. So in this case, the longest carbon chain is actually 7 if you count across the top, but you'll notice that the name is hexane 2-ol in the end. And the reason for this is when we name the longest chain or the parent chain, it has to include the functional group. It has to include this OH on it, which is why our longest chain actually ends up being 6. Keep that in mind whenever you are naming the longest chain. So that means our chain is hexane for 6. All of the prefixes are here. You then want to determine the substituents you have, any functional groups, and you go about naming those the relevant suffixes. The substituents, and these are specifically your side chains and halogens, will come at the front of your name and are lower priority compared to your functional groups. So anything above your alkyl halides and your alkyl groups will be at the end. For example, your alcohols, carboxylic acids all come at the end of your chain as a suffix, and you number based on those. In terms of locants, yep, Sumya's got a question. So, sorry, just to confirm, the longest chain must have at least one functional group. Not necessarily true. If there is a functional group, then you must include it in the parent chain. But if you have no functional groups, then you don't necessarily have to include it because there wouldn't be a functional group. So it's just only if you have a functional group, it must be on the main chain. Okay. Then if you have multiples of any functional group or substituent, you use the prefixes of mono, di, tri, tetra. So that quantifies how many, for example, alcohols you have. A diol means you have 2 alcohols on the chain. And you then apply locants. So locants tell you where exactly something is on the chain, which is why in our name, 3-methyl, 3-propyl, hexane, 2-ol, we have locants directly in front of everything they're describing. The 2 is describing that our alcohol is on carbon number 2. And why have we decided to number the chain from the bottom going up, 1 then 2, as opposed to starting from the top and going 1 then 2? What's the reasoning? Great, Zoe. So it has a higher priority, so you want the lowest number on the alcohol, and it makes the most sense here. And then based on that, as you number around, you see that there's a methyl group coming off of the 3rd carbon, which implies that this is a 3-methyl and a 3-propyl for 1, 2, 3 carbons. Why have we done methyl before propyl? Alphabetical order, good. And that's how you name basically any molecule. There's obviously, you can go in depth with every molecule and do this, but this is the main framework, and just to crash through it. Just to summarize the functional groups, we have alkanes, enes, and ines. We should know that the general formula for each is represented as 2n plus 2 for the hydrogen, 2n for the hydrogen, and 2n minus 2 respectively, because for each time you add on a double bond, you're taking away 2 hydrogens. So your number of hydrogens decreases by 2. Each of these can be described as saturated or unsaturated. Saturated meaning that you have only single bonds between any 2 carbon atoms, or the chain is completely saturated with hydrogens. There's a maximum number of hydrogens on it. Or unsaturated meaning that you have at least 1 double bond or triple bond. And those would be your alkenes and ines. What's the significance of saturation in terms of reactivity? What's more reactive, what's less? Saturated or unsaturated? Good. Alkenes are more reactive, and that's the reason why saturation is important, because when we talk about the chemical properties, then we're going to have to worry about alkenes and ines much more than alkanes, which is why when you draw your flowchart, you have so many more reactions with those. Okay. Alkyl groups. So whenever you have carbon chains coming off the main chain, we call them an alkyl chain, and we name them based on how many carbons there are. If you have 1 CH, we have your 1 carbon coming off of the main chain, it's a methyl, 2 ethyl, 3 propyl, so on and so forth. Caption language to English. Okay. Continuing on, when you're ordering these, as I said before, they should be in alphabetical order if you have multiple. And also, if you have 2 of the same side chain coming off, for example, 4,4-diethyl, please note that you always have to show as many locants as there are whatever you're describing. So if it's diethyl, you have to put 2 locants to describe where each of those ethyls are, even if they're on the same carbon as they are here. So 4,4-diethyl would tell me there's an ethyl, well, there's 2 ethyls, one on carbon 4 and the other one also on carbon 4. If you just said 4-diethyl, trying to say that these are both on carbon 4, this is nonsensical. You're telling me where one of the ethyls are, but not where the other one is. So with your locants, always think of them as tally marks. You need as many locants as things you're describing. Okay. Cycloalkanes, enes, and ines. So sometimes you can have what we call cyclic structures, where the carbon chain forms a ring, and the chain essentially attaches at the 2 ends together to make a ring structure. The general formula for CnH2n is that of a cycloalkane. So what would this be a isomer of, and what type of isomer is it? An important relationship to make. What would this be an isomer of? An alkene, and what type of isomer is that? For bonus marks. Functional. So this is a functional group isomer of alkenes because it has the same general formula. You can always swap between them. We'll talk about isomers more in a second. Okay. Don't really need to worry too much about benzene, phenyl, and benzyl, but as long as you can recognize a benzene ring, you will see it in your condensation polymers. That's probably enough for now. Just recognize that it's a benzene. Halogenated organic compounds, these have similarly a prefix, Halo is the prefix, so it's either bromo, chloro, fluoro, or iodo for each of the halogens. They are named the same as your alkyls. They come at the start of the chain. Do halogens versus alkyl halides versus alkyl, so your side chains, do one of these have higher priority or do we treat them the same? Alkyl versus alkyl halide. We're naming them. How do we treat them? I think technically alkyl is slightly higher, but when we're actually naming them, it doesn't really matter. They both come in front and we order them alphabetically. It doesn't really matter to us. So they kind of get grouped into the same level of priority. Okay. Just an important point here. Whenever you have multiple of the same thing on the chain, or you have a lot of things on the chain, you always find the correct way to number from the first point of difference. So what we mean by this is if we look at these two molecules and we're going to name them, we have a methyl here, and we have an ethyl here, as well as a bromo. So when we name this alphabetically, it would be locant bromo, locant ethyl, locant methyl. And you find out the lowest possible numbering from the first point of difference. So if you were to try a number from going from left to right, 1, 2, 3, 4, 5, 6, 7, 8, the numbers are 3, 4, and 6. Whereas in the other example, the lowest numbers are 3, 5, then 6. So because the first point of difference between the numbers, the first two numbers, 3 and 3, are exactly the same. The first point of difference is the 5. And so this means that this is a higher arrangement of locants and wouldn't be correct in this instance. The other one would be. So looking at these other ones, look at option A and option B for the top two. Which has a better priority? Which is the correct priority? A or B? Got a lot of B's. Would someone like to explain why it's B or why it's A? Got a bit of swapping. Okay. So I would say it's A. And the reason is we're choosing from the first point of difference. So if we're looking at all the locants here, it's 2, 5 for this fluorine, and 6, 6. 2, 5, 6, and 6. Whereas option B is 3, 3, 4, then 7. So the first point of difference is the 2 at the very start, and that decides it already. We don't have to worry about any of the other numbers that come after it. The first point of difference is what decides our lowest order. Okay, moving along. So now we're on to the functional groups. Alcohols. We should know that an alcohol is OH. Whenever you see something represented by an R, this just means a carbon chain generally. Alcohols have a general formula of CnH2n plus 1 OH. It can be derived from the formula of an alkane because you're simply swapping out a hydrogen with a hydroxyl. That means you're minusing off one H from the H2N plus 2. You're taking away one of the H's and replacing it with an OH, which is why we get to H2N plus 1 OH. Richard, the intensive from yesterday will go up just in a few days' time. Okay. The suffix for alcohols is ol, so methanol would be a carbon chain of 1 with an ol, meaning alcohol on it. Okay. We also call the OH a hydroxyl. So be clear that this is a hydroxyl group and you refer to it as such. Whenever you see an OH, for example, in an alcohol or a carb acid, it should be a hydroxyl. Primary, secondary, and tertiary alcohols, the rule is how many carbons are attached to the carbon attached to the hydroxyl. It is not how many carbons attached to the oxygen. That doesn't make sense. There's always only going to be one. It's how many carbons are attached to the carbon attached to the oxygen. So it's 1 for primary, 2 for secondary, 3 for tertiary. Okay. Aldehydes versus ketones. What's the difference? Type in chat. What's the difference? Okay. I like Zoe's answer. Ketone in the center versus aldehyde at the end. And the terms that we like to use are terminal and non-terminal. Terminal means at the end of the chain. Non-terminal means anywhere in the middle of the chain. And what's on the end or what's in the middle? It's a carbonyl group. So this C double bond O is referred to as a carbonyl. So now we have hydroxyl. We also have carbonyl, describing these individual components. The suffix for aldehydes is al. We never need a locant for aldehydes. Why? Always on the end. So what number will it always have? 1, because it's super high priority. This aldehyde is like one of the highest priorities apart from carb acid. So it's always going to take a number of 1 and be on position number 1. Doesn't need a locant. Ketones, do you always need a locant for ketones? Yeah, yeah. What if I said it's no? Okay, so we've got some interesting answers. So yes, propanone, I like that. E. So propanone, you won't need it because you cannot move that carbonyl to the first carbon. It'll just become an aldehyde. There's one other example. Butanone. Butanone as well. Because if you have butanone, I'm going to draw it in skeletal just for pace. Butanone is going to be butan-2-one no matter what. You cannot have butan-1-one. That wouldn't make sense because that's just butanal. So be clear on that. 2 of the ketones don't need locants. Don't write these locants when you have them in your exam. And just going back to Sumya's comment on eth, you couldn't have ethanone because that would just be ethanol. You can't possibly have a non-terminal carbonyl on a carbon chain of 2. Yeah, all good. Great. Moving along. Carboxylic acid ends in oic acid and is the combination of a hydroxyl, and carbonyl. So if you're not already incorporating these terms in your discussions, carbonyl, hydroxyl, really high yield things to take away, elevates your response. Anything ending in oic acid is your carb acid. Do carb acids need a locant? No, always on the end of the chain. So always have number 1 as well. These are relatively straightforward. Amines, everyone's death. Everyone hates naming these, but it's actually not too bad. You just need to be clear in your mind that there's primary, secondary, and tertiary amines. Each of these is slightly different, but the system for primary, secondary, and tertiary amines is different to that of alcohols. It's simply how many carbons are attached to the nitrogen. 1 for primary, 2 for secondary, 3 for tertiary. The suffix for amine is amine, makes your life a bit easier. And amines generally are represented by NH2. So this is an amine, generally speaking, for a primary amine. And naming primary amines are really easy. For example, if you have something like this, you count the chain. What's the name of this molecule here? Everyone type in chat. And the only thing that differs them is the number of carbons attached to nitrogen. So Rachit, the amount of carbons wouldn't change you from primary, secondary, or tertiary. It would just change the parent chain length or change the side chain length. Okay, so everyone said pentanamine. I'm going to say we're all wrong. How can we improve our responses? Good. Zoe, pentan 1 amine. We have to be specific because what if this amine was on the second carbon? Then we lost our mark because we've just said pentanamine. We don't know if it's on the second carbon or even on the third carbon. So always have a locant. And once you've put your locant in, ask yourself, can I then get rid of it? Is it redundant? So that's your primary amine, where you only have one carbon attached to the nitrogen, only one. Why is it one? Because it is on the first carbon on the end of the chain. 1, 2, 3, 4, 5. It wouldn't make sense numbering from right to left. Otherwise, you'd end up with pentan 5 amine, and that's a much higher number. So you'd want to make it as low as possible. Okay, so that's your primary amine. Secondary amine suddenly becomes a little bit harder. Something like this. So how do you name this? A secondary amine. Type in chat. Is that a question? Do we need a locant? What do you reckon? Yes or no? Yes, no, yes, no. So in this case, the name that Zoe's put is actually 100% correct. It is N-methyl ethanamine without a locant. Without a locant. And so let me explain this name, first of all, how we get it. If we did have a locant, it would be ethan 1-amine because it's on the first carbon. Let's explain how we get this. So the first thing you need to do to name an amine is find the longest chain length. And you find that it is a carbon chain of 2. So your longest chain is 2. That is your parent chain. That correlates to the ethane part. It is an ethane chain because it's only single bonds between the carbon, only 2 carbons. Then you name the functional group, amine, because it's an N in the middle. You say that the amine is on the first carbon, so it's 1-amine. Then you name whatever other carbon chains come off the nitrogen, and this is only going to happen in a secondary or tertiary amine. N-methyl refers to a methyl CH3 coming off of the nitrogen. N is a locant we only use in nitrogen-containing organic compounds, so amines and amides. This is telling us N-methyl is saying there's a methyl on the nitrogen. And that's how we name it. Why don't we need this locant? What if we had the nitrogen flipped around and placed on the other carbon? What would that be called? Would it be any different? Oh, as in the whole thing. Sorry, kind of confused you. This whole unit, say it flipped onto this carbon. Would it be any different in how we name it? No, no difference. It'd be exactly the same. N-methyl ethan 1-amine. So when we have the same configuration, there's only one configuration possible, we can get rid of locants. That's the only case where we don't have one. Same as with butanone. So it becomes N-methyl ethanamine. So there's only one configuration possible, Richard, because if you move this amine and its methyl to the other side, it would still be attached to an end carbon and therefore still have the number of 1 and then 2. Whereas in the current case, it's 1 and then 2. It would still be ethan 1-amine. So regardless, it's the exact same. And that's why you can call it redundant. So for naming tertiary amines, you take the exact same process. So let's take something like this. Oh, that's not tertiary. This is tertiary. You find the longest carbon chain. So it's going to be either of these ethane chains. So you take ethane, and because it's an amine on the first carbon, usually you would put ethan 1-amine, but we know it's going to be redundant. So ethan amine is fine. Then we can put in front of it our Side chains, we have a methyl and an ethyl coming off of the nitrogen, giving us N-ethyl, N-methyl ethanamine for our tertiary. So you name it sort of similarly to how we do a like normal hydrocarbon, except the side chains will be on a nitrogen and you name them with the locant telling us it's on the nitrogen. How else is it fine to have a locant anyways, even though it's the same? So it depends how harsh your school is. If you're at a school that marks harsh, you'll lose marks for putting redundant locants, but if you're ever in doubt, just leave it in. Okay, cool. Let's keep moving. And just to be clear, with punctuation, I should have made it clear as well. Whenever you separate a locant from a word, you have to use a dash. So it's locant dash word. But whenever you have two locants being separated, so locant and another locant, you use a comma. And if you have two words, you don't use anything between. There's no punctuation. So locant dash word, locant comma locant, word, word. Amides, similar naming scheme, slight difference. You have to acknowledge the carbonyl in an amide in order to find the parent chain. So the main difference for amides is that it doesn't matter what the longest chain is, the parent chain is always predetermined. So I'm just looking for a good case. I might make a different one. So let's say we extend this here. This amide at the top. What do we name this amide? In the chat. Treat it as if it has an extension on the chain here. N-methyl ethanamide. Wrong way. Gonna swap it. Yeah, I like that. So it will be in fact um, N-ethyl methanamide because the parent chain in an amide is determined by where the carbonyl is. It doesn't matter whether it's longer or shorter than the other chains coming off the nitrogen. That will fix your parent chain. So the parent chain here is methanamide because an amide is made up of a carbonyl and an amine. So this is your carbonyl once again and an amine. But you can once again have primary, secondary, and tertiary amides depending on how many carbons come off the nitrogen. So if there's one, it's as primary. If there's two, it's secondary, three, tertiary. So this is a primary, secondary, or tertiary amide in the chat. Once again, primary, secondary, tertiary. The one in the box, secondary. Great. Good. Esters finally. So esters are made up of two parts. We write them as two separate words, alkyl, alkanoate. What is the alkyl describing? What is the alkanoate describing? Because we know how esters are made. What functional group is responsible for making each of these parts? We need to be clear on this. Alkyl, alkanoate. Okay, got a mix. Alkyl is from alcohol. Alkanoate is from alkanoic acid or carboxylic acid. Same thing. Be clear, because otherwise you will mix up your names. When we name our esters, the alkyl component will just take on the chain length of the alcohol you used to make it, and the alkanoate will take on the alkanoic acid that makes it. So how do we name an ester like this? What is this? Everyone in the chat? Ethyl ethanoate, double check it. Ethyl propanoate. Just being careful that you do include the carbon that is involved in the, do include the carbon that's involved in the ester group itself. So the ester function group is actually just this COO part in the middle. That's your ester. And on either end is the two chains. And you do include the carbon included in the ester. You can always figure out which side is the carb acid side because it will have the double bonded O on it. That is your carb acid. And this is your alcohol side, which means this is your alkyl and this is your alkanoate. Okay. Function group summary. You don't really need to know the prefixes. For the most part, HSC won't assess multiple function groups. So the most you'll get maybe at worst, I mean, you'll get the halogens coming in front. The worst you'll get is maybe a hydroxy, if you ever see it internally, where you see maybe an alcohol and you see a carboxylic acid. You might see a hydroxy carboxylic acid. But in most cases, you're only dealing with the suffixes for these. Okay, isomers. An isomer is a molecule that has the same molecular formula but different structural arrangement of atoms. 3 types of isomers: chain, position, and functional group. A chain isomer is where you have 2 molecules that have the same number of all the atoms, but they have a different chain length. So chain length of 3 carbons as opposed to chain length of 4 carbons. Position isomer is where you have the same chain length, but something is moving onto a different position on the chain. For example, chlorine moves from the first carbon to the second, and a functional group isomer, the hardest one to spot. We have functional isomer is where you have, for example, a aldehyde changes into a ketone or vice versa. The other important pairs for functional group isomers are carboxylic acids and esters. And as we said before, alkenes and cycloalkanes. That's a really common trick one they like to throw in with the cyclic structures. Okay, and just going back on the esters, I'll re-explain esters again when we get to it later on, but I'll keep moving just so we get through everything. Okay. Moving on, inquiry question 2. So hydrocarbons, how can hydrocarbons be classified based on their structure and reactivity? So now that we've laid the foundation, what we've finished in that first 40 minutes is all the naming and all the structure. So now on each of those individual functional groups, we're going to build a tower describing its properties in physical and chemical properties and how they can be used in real life. So each of those, we're going to do hydrocarbons, we're going to do alcohols, we're going to do all the acids and bases, so amines, carboxylic acids, and we'll also talk about ketones, aldehydes, and esters at the end. That's kind of how we're going now. Drawing, you should be able to draw any organic compound using any of structural, condensed structural, and skeletal formula. In your exam, you're most commonly expected to use structural formula, the full thing. So if you're ever asked to draw something, that is what you draw it in. Do not draw by default in condensed structural or skeletal, you'll get marked down. So draw in full structural if ever in doubt. That's your golden rule of thumb. And in terms of the differences, I'll just show them in terms of butane. So butane, for structural, you're showing every single bond, every single carbon, every single hydrogen. So everything is shown in structural formula. Let's make it more interesting. We'll go butanol, butanol, because this allows me to talk on something that peeves me. You'll notice that on my butanol, I've drawn a bond between the O and the H. You can lose marks for not showing the bond between the O and the H in a structural form. So just do it. You don't want to risk it. Just show the bond fully. Condensed structural, there's 2 ways you can represent condensed structural. You can either do it in the really condensed way, where you don't show any bonds at all. Wow, my pen is playing up. Okay, CH2OH, or you can show them with bonds between the carbons still. Like this. You can do that for condensed. So just be clear on the difference between those. And then finally, so these ones are your condensed structural over here. And finally, skeletal, you can do 1, 2, 3. every time you have an end of a line or a intersection or a corner, that is representing a carbon. And to show the butanol, we can put it on here, OH. Okay, be clear on those three different ways of drawing. Hydrocarbon shapes. Okay, back to module 1 of year 11. You need to understand where the hydrocarbon shapes or molecular geometry is all derived from. We cannot talk about intermolecular forces. Do we need to use rule of Skeletal? Not necessarily. It's okay. As long as you can draw straight lines, it's fine. For hydrocarbon shapes, you need to understand VSEPR theory. And if you don't understand this, you cannot understand anything about physical properties at all. So if you're struggling at the moment with intermolecular forces and figuring out when you can find dipole-dipole or H bonding or just dispersion, if you don't understand this, you will never be able to figure out anything beyond what we're going to talk about here. Your progress in the module stunts. So you need to re-understand your module 1 content. What they talk about in module 1 is a theory called VSEPR theory. Can anyone describe VSEPR theory quickly in the chat or even unmute? What is VSEPR theory? What does it tell us? Kind of on the screen, but put in your own words. So it helps to find out the shape of molecules. Yes, so Sumi is onto it. When electrons want to stay as far away from each other as possible. That's the repulsion theory. Okay. So essentially, every single compound molecule has bonding groups and lone pairs. Bonding groups and lone pairs. The separation between a bonding group and lone pair will always be at the maximum possible angle because every single lone pair is made up of 2 electrons and every single bond is made up of 2 electrons as well in a covalent bond for organic chemistry. It's always going to be a covalent bond. So naturally, if these are both negatively charged things, the lone pair has 2 negative electrons, bond has 2 negative electrons, they do not want to come anywhere near each other. They will repel. And if you, for example, only had a lone pair and 1 bonding group, they would repel maximally to make a 180-degree separation. That's what VSEPR theory is telling us. If you then have 3 bonding groups, the separation would be 120 degrees. And if you have 4, you finally get a 3D structure, which has 109.5 degree separation approximately. And these make up our 3 major molecular shapes that you must know. What are the names of the shapes? So the one where there's 2 bonds, 3 bonds, and 4 bonds. What are these? Linear. So linear is this one here. What else? What's the one with 3 bonds? Be specific. Trigonal is not good enough. Planar is not good enough, but trigonal planar is good enough for the second one. Be specific because they are different things. Trigonal planar. And finally, we have tetrahedral. So those are your 3 families of molecular shapes. All your bent, all your bent structures and your trigonal pyramidal structures, these are derived from these 3 families. How do you get to a bent structure? There's 2 ways. How can you get to a bent structure? When do you have bent? No, not to do with hydrogen bonding. That's intermolecular force. Zoe's kind of the closest. So Richard, you mean more than 2 bonding pairs? Not as like you would need 2 what we call electron groups. We would need more than 2 electron groups because an electron group is either a lone pair or a bond. Lone pairs. That's all you need. So we need, not more than 2 lone pairs. That's not possible to have bent. We need at least 1 lone pair or in one case 2. So let me show you what I mean. If you know these 3 shapes, you can find out your other geometries from these. So let's see what happens if we replace one of the bonds. So at the moment, everything I've drawn is bonding groups. These are bonds. Let's say I replace one of the bonding groups in trigonal planar with a lone pair. Are the two bonds at the bottom just going to start to flick up now and be at 180 degrees? Will that happen? No. They'll still be repelled by the top two electrons downwards because that's still what VSEPR theory states. Lone pairs, also two electrons, they'll still push them down. In fact, they push them down even more. Don't need to know that, but it'll still be pushed down. And because of that, you no longer have a bond at the top. So you can't describe this as trig planar anymore. You just have two bonds in a bent shape downwards. So this ends up being a bent molecule because your bonds are bent, being pushed down by a top lone pair. This is the first case where you can have bent, where you have one lone pair and two bonding groups. I say bonding groups because one of these bonds could be a single bond, it could be a double bond. It would be a slight change in angle. I believe the angle between the lone pairs and the bonds slightly exceeds 120. It'd be like 121 or something, but not overly important. Just understand that there's still going to be a repulsion, and this is your first possibility of a bent geometry. Now, if you have just two bonds and lone pair. So then what about tetrahedral? What happens when we replace one of the bonding groups with a lone pair? What shape do we get? Becomes a pyramid. So what do we call it? Three bonding groups plus one lone pair. It is a pyramid, trigonal pyramidal. Trig pyramidal. If we replaced one of those bonding groups with a lone pair, because that top set of electrons, that lone pair, is still repelling the bottom three bonds all downwards. They'll make a little tripod shape at the bottom, which is your trig pyramidal. So the last case that's really important to us is we can replace a further one of those bonds with another set of electrons to make another lone pair. Now, what is this final shape? Where we have two bonding groups and two lone pairs. Bent once again. And this is the trick that once you understand how you derive these, it makes sense. Sometimes you can have bent from a trig planar origin, and you can get bent from a tetrahedral origin that have slightly different angles, but they're both classified as bent. And it's just depending on how many bonding groups and lone pairs you have, you can always figure it out. Okay. So let's keep moving. This is a summary of what I just talked about. This is what I was saying. If you have two electron pairs, then it's going to be linear. If you have three electron pairs, then you're going to have trig planar, replace one of those bonds with an electron pair, it's bent. And for tetrahedral, that's four electron pairs, replace one of the bonds with a lone pair, becomes trig pyramidal, replace two of them, it becomes bent. You don't really need to know beyond 4 for mod 7. So then the question is, how can you figure out the bond geometry? For number 2, what is the molecular geometry around carbon 2? Trig planar. Good. What about number 3? Bent, because there's two lone pairs and two bonds. And then what about CH3 on the end? What's the molecular geometry around the carbon? Not pyramidal, not linear. Think about it. CH3, tetrahedral, because what we actually have here is a carbon with 1, 2, 3 bonds to 3 hydrogens. It's condensed here, so just be wary. I was asking about the carbon specifically. Okay. And the reason why that's important for intermolecular force is when you're understanding symmetry in your your polar bonds, it's important to understand the shapes. Zoe asks, so are the H just all 3D in space? Yes, they would be 3D because it's tetrahedral. It wouldn't be planar. Okay, homologous series. These should be somewhat familiar. The first three are important, I would say. The other ones you can all derive. Some of these are a bit strange, but you can always derive out general formulae if you know what alkanes, enes, and ines are, and you can replace the hydrogens that you remove with the functional group that you're placing in. Richard, does it being H change anything? No. So all you're worrying about in molecular geometry is how many bonds or lone pairs are around the atom that you're worried about. In the case of carbon, there's always going to be 4 electron groups, and usually it's going to be 4 bonds. In a structure like nitrogen, so say for example ammonia, what would the molecular geometry of ammonia be? It's got 1, 2, 3 bonds to H, but it also has a lone pair on top. So it doesn't matter what is bonded to the atom in the middle, as long as it has those bonds, you count them as bonding groups, and you count the lone pairs as well to figure out what kind of geometry this is. This is trig pyramidal. Okay. So moving along. For homologous series, what is a homologous series? Type in chat. How do you define a homologous series? Homologous series. Different carbon chain length, but same functional group. Yes, and same position of functional group too. Has the same position. Good. And they tend to have similar properties, similar chemical properties because of the same functional group. And the physical properties will slightly change throughout the homologous series. We'll talk about that more in a second. So for trends within a homologous series, you're expected to be able to explain boiling point, melting point, solubility, and reactivity at the very minimum. And most exam questions will ask purely on these because it allows you to link together intermolecular force, your discussion of molecular geometry, ties all together. We'll talk about reactivity in a second. So, more module 1, you need to know all your intermolecular forces, dispersion, dipole-dipole, hydrogen bonding, ion dipole. Hopefully, these are somewhat clear. If not, let's go through them once again. Also, being clear on intra versus intermolecular. Intra is within from the Latin origins. Inter means between. When we're talking about physical properties, everything is in terms of intermolecular force. Basically, at no point when you're talking about boiling point, melting point, solubility, you be talking about covalent bonding. It's all about the intermolecular force between molecules. You're talking in terms of dispersion, dipole-dipole, H bonding, and ion dipole. So let's first of all understand what makes a molecule polar. What's the electronegativity difference that we need for a bond to be polar? Specific number. It is important to know. 1.15 is pretty big, bit smaller. 0.5, pretty much. I mean, probably different source. I've always known it as 0.4. 0.5 would exclude, I mean, 0.5 is around it, but 0.4 is what I've always taught. And what I mean by that is when you look at the electronegativity of 2 atoms in a bond, for example, you look at carbon and it's bonded to hydrogen. Hydrogen has an electronegativity of 2.20 and carbon has one about 2.55. So when you're comparing the electronegativity difference between carbon and hydrogen, the difference is simply one minus the other, giving us 0.35 as our electronegativity difference. That tells us that this bond is nonpolar. And that's important to know for every single common covalent bond that we come across in organic chem. Anything bonded to carbon from the halogens or any of the common non-metals, and anything bonded to hydrogen, we should know if is that polar or not. And then in terms of the other thing that makes a molecule polar and is more commonly neglected in schools is asymmetry. What I mean by this is that when you have two polar bonds, for example, oxygen to carbon and oxygen to carbon in what we like to call carbon dioxide. Hopefully you've seen this molecule before. The molecule has polar bonds. Carbon to oxygen is polar. However, because it pulls evenly on electrons either way across the molecule, it is a symmetrical molecule. The dipoles actually end up canceling out, and the molecule ultimately ends up being non-polar as well because it is symmetrical. So these things are important to understand for using our understanding of symmetry of molecular geometry from before will allow us to figure out is a molecule symmetrical or not. And without that step, you can never figure out for sure is a molecule polar. So let me give you another example. Cl, C, Cl, Cl, Cl. Is this molecule polar or not? Yes or no? But it has polar bonds. Why is it not? Why is it not polar? It is symmetrical, not symmetrical. It is symmetrical. Even though you have CCl, which is polar, because rotationally this molecule is symmetrical, all the dipoles will cancel themselves out, and it results in no polarity observed on these bonds. What if I changed one of these to a hydrogen? Now is it polar? Yes. So now it's polar because this bottom of the molecule with these chlorines, they all pull electrons with a downwards vector, whereas the carbon to hydrogen doesn't pull electrons at all. So it results in a negative dipole around each of these chlorines and a positive around the hydrogen. And this is how we start to get our understanding of dipole-dipole. When you have polar molecules, there will be an uneven distribution of electrons permanently because these polar bonds, where there's electronegativity difference, the more electronegative atom is pulling electrons away in such a way that they gain a slightly negative charge. How do we define what a dipole is? What is a dipole? Define it. So what is a dipole? And in response to Richard, why doesn't the hydrogen to carbon bond pull electrons? So the carbon would, because the carbon is actually slightly more electronegative, the carbon would very slightly pull downwards, but nowhere near with the strength of the chlorine to carbon bonds. So it's whatever is more electronegative will pull electrons slightly. So what is a dipole? We don't really have a working definition yet. Dipole means something with a partial charge. Partial charge, and we often represent them with the delta plus, delta minus. We have to understand that a dipole is not a complete charge. So when we normally see, for example, Cl minus or F minus, that is a halogen with a complete 1 minus charge, or sulfate has a 2 minus charge. When we're talking partial charge, you can think of these as charges that are like 0.1 plus or 0.2 minus. They're very small charges. And whilst they do interact with each other, they're not as strong as a complete charge. So let's come back to our discussion of intermolecular force. Now they've sort of set the scene about how do you know if a molecule is polar or not? We now know you have to have a polar bond, which has an electronegativity difference bigger than 0.4, and you need the molecule to be asymmetrical rotationally and if you were drawing lines. So the four intermolecular forces: dispersion force. Dispersion force forms from the random movement of electrons. So if you have movement of electrons from one side, for example, you have this atom here, and it only has one electron, say it's a hydrogen. In any given moment of time, the electron could be up here. It could have moved back over here. It could have gone over here. It could go anywhere, in theory. So depending on where the electron density is in a given moment in time, there will be a difference in charge on different sides of the atom. And that is why we call dispersion force. It's how the electrons are dispersed at any moment in time, dispersed towards one side or the other. And we say it's temporary because it's purely based on where the electrons decide to be in that millisecond frame of time. They can move to the right. In the next millisecond, they're all on the left. Then they're on the top, on the bottom. It doesn't matter where they are, but the point is they can be anywhere, and that can change at any given moment. So when the electrons move to the top left, for example, what dipole will form in the top left? Negative. You would say you have delta negative and delta positive. On the other end, because the electron density left went away from the bottom right, leaving a positive charge. So say that the same thing happens on this one. You have the electrons move to the top left. That results in a delta negative and a delta positive. Dispersion force can then form between wherever you have a positive and a negative dipole. And that is what we call electrostatic attraction, the attraction between opposite charges. Electrostatic attraction. Okay, so that's dispersion force. We have to also understand that at any moment, this electron up here could decide to run away and go back to the other side, changing the dipoles to negative and positive, and hence this dispersion force would no longer form. That's the idea with dispersion force. It's temporary, it's weak, and it happens with absolutely everything. As long as you have electrons, you will have it. And so it happens in every organic molecule, no matter what. If you ever get asked a question, it will have dispersion force, regardless. Okay, so then I'm going to draw a big line through here. Things above this line will only form if you have a polar molecule. That is the condition of entry, the admission ticket to having dipole-dipole and H bonding. You cannot have it if you don't have polarity in your molecule. So it's basically what we just talked about. You need to have a polar bond and you need to have asymmetry in your molecule in order for the electrons to be permanently dragged away. In this illustration, it's showing they're dragged towards one side, giving you a permanent dipole. So this would be a more electronegative element, like oxygen is pulling on this side compared to hydrogen, or let's make it carbon on this side. The electrons are moving towards the oxygen because it's more electronegative, giving it a negative dipole and leaving behind the carbon. The carbon's electrons are being pulled away, giving it a positive dipole. This is how we form our permanent dipoles. And the same thing happens in this one. OC, delta negative, delta positive. So the dipole-dipole interaction forms between two partial charges. It forms between the two permanent dipoles. Forms between the oxygen and the carbon. Positive and negative electrostatic attraction. That is your dipole-dipole. It is stronger than dispersion force because these dipoles will be greater in magnitude. Any questions so far? Dipole-dipole dispersion. Okay, let's keep going. So then you take another step up. When can you form H bonding? In the chat. When do you form H bonding? When there's FON attached to H. Good. So FON, NOF, whatever you want to say. But you need a nitrogen, oxygen, or fluorine attached to hydrogen. So this A has to be one of, let me change color, has to be one of N, O, or F attached to a hydrogen. Why? It's because hydrogen has a relatively low electronegativity, and nitrogen, oxygen, and fluorine have the three highest electronegativities. I know chlorine is pretty high as well, but for our purposes, we consider it as nitrogen, oxygen, and fluorine have the highest three. So when you bond a hydrogen to a nitrogen, the electronegativity difference is somewhere in the order of like 1 point something plus all the way up to about like 1.7, 1.78. It's like a big, big difference, which means the pole that you form, because the hydrogen is so not electronegative, the pole that you're able to form is much stronger. The dipole is much stronger compared to a normal dipole-dipole. So H bonding is just a stronger version of dipole-dipole. The mechanism is exactly the same. You're having the pulling away of electrons from the non-electronegative element, and that allows you to form H bonding between hydrogens and lone pairs. Could I re-explain what a dipole charge is and when it occurs? So a dipole charge is a partial charge, and you form a dipole whenever you have electrons moving, whenever you have electrons located more on one side of an atom than the other. So if you have, let's say this circle is representing an atom, if you have more electrons on the right side compared to the left, this will form a dipole on the right because it will have more negatively charged electrons compared to the left-hand side, which will be left with a positive dipole. So this is what we call a dipole here. And you form this in dispersion force. If electrons decide to randomly all move to the right or randomly move to the left, you'll form dipoles on either side. In a permanent dipole, where there's a polar bond, the electrons will move towards whatever is more electronegative. I should have defined what electronegative actually means. So what is electronegativity? Type in the chat. What's electronegativity? Affinity to steal electrons. Yeah, I would say, like, simply put, how strongly an atom attracts electrons, how strongly an atom sucks electrons towards itself. So if you have high electronegativity, that atom wants to pull electrons into itself, right? In response to the question about dispersion, London, and the diagram with positive and negative charge, I'll do the dispersion force diagram one more time. I think I did the diagonal vectors. I shouldn't have done it that way. I should have done it horizontally. So say for dispersion force, you have electrons in each of your atoms. An electron can decide to move to the left. I won't do diagonal, It can decide to move to the right at any given moment of time. And if an electron is on the right and there are more electrons on the right than the left, you should have a negative charge on the side with more electrons, giving a negative charge on the side with more electrons. The same thing can happen in the other molecule, which would result in a negative charge there. And the opposite side of that same molecule would have a opposite charge because it essentially lost its electron density. It has less electrons than the right, which results in a positive charge because there are less electrons. And the same thing happens in both. And dispersion, therefore, is the attraction between those positive and negative dipoles. Hope that makes a bit more sense. Okay. And lastly, ion dipole is the attraction between an ion and a permanent dipole. So this is stronger than H bonding because you're not just doing two partial charges attracting together. You're taking a full charge and you're attracting a partial charge. So it's always going to be that an ion dipole bond is stronger than a H bond. Okay, here's the mechanisms. And the hierarchy is important to remember. It goes dispersion, dipole, dipole, H bonding, then ion dipole in that order. Okay, so what determines boiling point, melting point? In terms of strength, so you're comparing bond for bond, it would be in that order. And obviously, if you have many dipole-dipole bonds, that could require more energy to break than a single H bond. So this is not really comparing number of bonds, comparing the same number, and it's comparing bond against bond. Okay. So why does this matter to us? We're now building up that we need to understand these forces in order to understand melting point, boiling point, solubility. because all of these physical properties are in terms of intermolecular force, how much energy it requires to break an intermolecular force. Let's talk about that more. What determines boiling point and melting point? If you have stronger intermolecular forces, you will have higher melting point and boiling point. You would need more energy to break bonds if they are stronger. AI companion, okay. And what determines solubility? Like dissolves like. So if you have a polar substance, it will dissolve in a polar solvent. If you have a non-polar substance, it will dissolve in a non-polar solvent. And it's because they form similarly energetic bonds, so that when you break and form bonds, the exchange is basically the same. Explain it a bit more in a second, but take away for now that strong intermolecular force means high melting point, boiling point, and like dissolves like in terms of solubility. They're your main governing principles. Okay. So for an alkane, what kind of intermolecular forces do you have? Let's take ethane. What intermolecular forces does ethane have? So dispersion. Does it have dipole-dipole or not? No, it won't, because it is a non-polar molecule. It only has non-polar C to H bonds. So it makes it non-polar. It will only have dispersion. Therefore, if it has only dispersion, the weakest type of intermolecular force, to expect its boiling point to be relatively high or low? Low. And should it dissolve in water? No, shouldn't dissolve in water because it's non-polar. And water is our most common solvent. It is a polar solvent. Water is HOH. What's the molecular shape of water? Two bonds, two lone pairs. It is bent. It is bent. Two bonds, two lone pairs. And because it's bent, where are the dipoles? Where's the positive dipole? Where's the negative dipole? So we have the oxygen at the top. Oxygen is very electronegative compared to hydrogen, meaning it draws in electrons. Therefore, the dipole should be negative at the top and positive around the hydrogens. Okay. In terms of homologous series trends, what happens as we increase chain length? What happens to boiling point in alkanes? And why? Increases why? Explain it. Give 30 seconds. You have 30 seconds to write a response to justify it. Why does boiling point increase as chain length or molar mass increases? Thumbs up for the best response. Okay. So I actually like Cheryl's response the best here. The one with talking about an increase in mass and amount of electrons. This is what everyone neglects to explain on this explanation. It is that as you increase chain length, yes, you're increasing molar mass, but why does that result in an increase in dispersion force? Everyone just jumps that step. Everyone says we increase molar mass, so we increase dispersion force. We need to explain the in-between part. So as you increase molar mass, you're actually increasing the number of electrons. And if you increase the number of electrons, this increases the potential to form temporary dipoles. Increases the potential to form temporary dipoles, or some people say it's an increase in polarizability. What this means is if you're comparing an atom that only had one electron flying around from one side to the other, now you're comparing it to something that has 100 electrons flying around from one side to the other. Would it be a greater dipole if just one electron moves a little bit from one side to the other? Or if 100 electrons all of a sudden goes from the left to the right? Does that kind of make sense? What we're getting at here? It's about the number of electrons. So if you have 100 electrons all go from the left or go to the right, that's a much greater magnitude of change in terms of dispersion force. And that's what I'm talking about in terms of potential to form temporary dipoles. More electrons means you have a greater potential to form these dipoles. And that is what leads to your increase in dispersion force. So bridging this step, these two steps, super commonly missed. That'll elevate your response. Then when you talk about increase in dispersion force, it means an increase in intermolecular force, which increases the energy required to break. And so you increase in boiling point. That's the full flow of things. Okay, continuing on. Explaining solubility. As we said, it's about like dissolves like and about the equal exchange of energy. So if you try to dissolve a non-polar solvent in a polar solvent, it's not going to work. Reason being, if you try to dissolve, for example, methane into water, all the waters are bonded to each other by H bonds. In order to break a H bond, that requires a lot of energy because breaking bonds will take energy. That's important. Breaking bonds consumes energy, whereas making releases energy. So when you're talking about dissolving, it's a process of breaking an intermolecular bond and forming a new one. Then that substance that formed that new bond is dissolved in the substance that it's bonded with. For that to be favorable, the amount of energy required to break the initial bond apart should be roughly equal to the amount of energy released when something new bonds onto it. That would be energetically favorable. But if the difference in energy is too big, for example, you have to break a H bond and the only energy you get back is the tiny force, the tiny energy you get from the formation of a dispersion force. That's not going to happen very many times. In fact, it would be very unlikely for it to happen. That's why we say like dissolves like, because it has to be an equal energy exchange. The amount of force required to break a H bond has to be replenished with force, with the energy from formation of a new H bond. Or if it's two things that are bonded together by dispersion force, if something else comes along, breaks a dispersion force and forms a new dispersion force and releases a similar amount of energy, that process can continue to happen over and over again. But if the difference is too big, it won't happen at all. Okay. Alkenes will have similar physical properties because they're both also nonpolar, same as alkynes, relatively similar. You're not really typically expected to differentiate alkanes from enes and ines in terms of boiling point, but they'll all be insoluble in water. Okay, chemical properties we'll get to in a second. Factors which affect intermolecular forces. If you increase the chain length, as we said before, you increase the number of electrons, increases the potential to form temporary dipoles, increases dispersion force, and you'll have more intermolecular force requires more energy to break, and so boiling point, melting point rises. How does increasing chain length affect solubility in polar molecules, and why? Say you have an alcohol. How does increasing chain length change solubility? Explain why. Zion, you're right, but explain why. It's the intermolecular force. Cheryl's on it. Cheryl's got it. The nonpolar part of the compound increases. So the solubility will decrease as you increase chain length. Because essentially what you're doing is if you had a polar component like an OH, and then you had a big non-polar chain, or you start with a short one. Let's say you just have a non-polar chain. The portion of the molecule which is polar is very large. So the majority of the forces acting here will be H bonding. But as you increase the length of the chain, the portion of the molecule that becomes non-polar is now much bigger. And the molecule is now more likely to form dispersion forces because of how much longer it's gotten in its non-polar part, which takes away from how much H bonding and dipole-dipole can form. So as you increase chain length in a polar substance, you'll have a decrease in solubility because the non-polar component of the chain is growing, which decreases the influence of the polar portion. Okay, the ability to stack or organize. So molecules that are straight and don't have any branches can stack together really easily at close distance, meaning the surface area interacting is relatively large. They have a much larger dispersion force. But if you have molecules that are branched, they cannot interact very closely. They're separated by all these side branches that keep them at an arm's reach. And the surface areas over which they interact are significantly reduced. So the dispersion force is less, and branched compounds will have a lower melting point, boiling point. In terms of position and access, molecules that have their functional group on the end of the chain tend to have higher melting point, boiling point than molecules that have their functional group on the middle of the chain somewhere. The best way to explain this is you imagine two pens or two sticks. If you were trying to get your two pens to meet right on the end, you can do it from this angle, this angle, this angle, any of these angles. These two pens can meet relatively easily. Very, very easy. You can even join them together in that way where they're bent back on each other. But if you have to make your pens meet right in the middle, you have to precisely place them on together to be interacting around the middle point. And there's very little variation with how this can happen, considering the functional groups are also sticking off the side. They have to exactly interact like that. There, 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 there. Very much locked in place. There's not very much variation. So it's harder to access functional groups in the middle of the chain because you require exact precision compared to functional groups on the end of the chain. And in response to Xian, packing is the same thing as stacking. Yeah, the ability to stack or pack. And we refer to it as crystallinity when we get onto it later in polymers. Okay. We also need to be able to compare the functional groups, boiling points, and we should have a hierarchy in our head of going from low to high, what the boiling points of substances are. So if you look at this list, ethane is less than ethanol, which is less than ethanol, which is less than ethanoic acid. And the hierarchy we build looks something like this, where you have dispersion force forming compounds at the bottom. They are lower in melting point and boiling point than dipole and dispersion forming compounds, and H bond forming compounds are at the very top. So this is your hierarchy in that order. When you're comparing melting point, boiling point, you always want to compare molecules of exact same chain length, not necessarily chain length, exact same molar mass. Why is that important? So we want to compare, for example, ethanamide versus it would be, for example, propane. Why do we want to compare molecules that have the same molar mass and not necessarily the same chain length? It'd probably even be closer to butane, to be honest. Why do you want to compare molecules that have the same molar mass, not necessarily comparing ethanamide and ethane? Not too sure. Okay, so when you're comparing molecules, melting point, boiling point, you always want to compare molecules that have the same chain length, that have the same molar mass, because that would mean they have the exact same dispersion force. And when you're comparing molecules in terms of their intermolecular forces, if you can say that the dispersion forces are the same, you can account for any difference on top of those dispersion forces in terms of dipole-dipole or H bonding. It means everyone has the same dispersion force. Any difference is then explained in terms of the other intermolecular forces. If you have different dispersion force, you can't accurately account for what the differences are. So you're always trying to compare molecules of same molar mass. When you're handling organic substances, in 30 seconds, you want to store like with like, wear PPE, clean up spills when you make them, wash your hands when you're done. And when you dispose, make sure things are labeled so you know what you're disposing. Dispose liquids and liquids together, and solids, so things of same state, and dispose of inorganic with inorganic and organic with organic. And don't put organic substances down the sink. Implications of hydrocarbon use. I'm not going to talk too much on these, but you need to know environmental, economic, sociocultural implications of use as well as obtainment. These are different things. So be clear that you need something for extraction and something for use for hydrocarbons from the earth. Here are some. Historically, you have much longer responses for this type of dot point, which goes up like 5, 6, 7 marks. These days, you still can get it. Some schools still like to do it, but it's being gradually phased out. It's like a kind of given question. It was given like 2019, 2020. Basically, every paper had it, to the point where now papers don't really bring it up as much. That's not to say it's not going to come up, but just less common. Hydrocarbon reactions. I'm going to go through the flowchart that I have. I'm not going to go through each individual reaction fully, but the idea is that you should have an idea of what you can react to form, go from one thing to another, and go all over this flowchart to make different substances. So this is the flowchart I have. I split it into inquiry question 3 for hydrocarbons, inquiry question 4 for alcohols, and inquiry question 5 for your organic acid and base. Let's go through the green section first. So for hydrocarbons, the main type of reaction you do is a addition reaction, and addition reactions occur onto your alkenes. You can add onto an alkene. You can add hydrogen. We call that hydrogenation. You can go from alkene to alkane. Actually, I'll explain the first mechanism just so you have a mechanism understanding. So if you're doing a hydrogenation, you're adding a hydrogen onto the chain, and you're breaking apart what we call a pi bond. So the pi bond is the bond in a double bond and triple bond, which is more reactive. A double bond has one pi bond and one sigma bond. Sigma and a pi. The pi bond is more reactive and is the one that you will react and break apart. And when you do so, the mechanism of this reaction is that the pi bond will effectively be broken and the electrons return to the carbon that they originated from. Because as we know, a covalent bond is made up of a shared pair of electrons. Because these electrons are now returned to their carbons, the hydrogen molecule is able to bond one atom onto each, H and H, and that forms your alkane. This mechanism is the same for all of your addition reactions, and there's 4 of them. Your hydrogenation, halogenation, hydrohalogenation, and hydration. What's the important consideration for hydrogen, hydrohalogenation, and hydration? What must you consider beyond the additions of hydrogenation and halogenation? What's special about these two? Think about the products. How many products can you form in a hydrohalogenation? Major, minor, so you can form 2. And it's because we have an unsymmetrical reagent. HX splitting into H and X, and H2O splitting into HO and H, which will attach onto the chain. Okay. And Markovnikov's rule. Do you want to type up what Markovnikov's is, Zion? just so everyone in the chat has it. What is Markovnikov's rule? Rich get richer. I guess that's one way to remember it. So essentially all it is that when you are bonding a unsymmetrical reagent onto an unsymmetrical alkene or alkyne, it's going to happen in alkynes as well. So keep in mind for all of your addition reactions, it can happen on a alkene more commonly, but they can also be preceded on alkynes. When you add a HBr into this chain, the hydrogen is more likely to bond onto the carbon with more hydrogens, 2 hydrogens as opposed to 1. And this is what Markovnikov's rule states, which means that the major product is the one where it has the newly bonded hydrogen on the carbon, which has more hydrogen. This is your major product. And you can form a second product because that HBr can go on this way, but it could also go on the other way. So flipped between the two cases. The H can either go to the end carbon or the middle carbon, and that will give us 2 different products, a major and a minor product. Just keep that in mind as well for your hydrohalogenation as well as hydration. This is also possible. So then going back to the flowchart, what we just covered there was we were able to go from an alkene to an alkane by using hydrogen and a metal catalyst such as PDO&C, nickel, or titanium. We can go from an alkene to a haloalkene. We can go from an alkene to a dihaloalkane by doing halogenation. That's just applying X2, meaning a halogen like chlorine or iodine. HX is our hydrohalogenation going to a haloalkane. We've also talked about going from, we can go from an alkyne to an alkene. And if we want to stop at an alkene, instead of going the whole way hydrogenating twice to an alkane, we can use a catalyst that we like to call Lindlar's catalyst, which stops our hydrogenation at the alkene. Going from an alkene, we can also go to an alcohol by doing hydration, and that's by using a dilute H2SO4 catalyst, which also acts as a dehydrating agent to make us alcohol. So you can also perform some other reactions with your hydrocarbons, specifically your alkanes. There's one last case for your hydrocarbon reactions, and that is the reaction between alkanes and halogens. You can do a substitution reaction where you apply UV light as your source of energy, and that will take you from an alkane and substitute out one of the hydrogens with a halogen. So the way it works, you can think of it as a football team. The people on the field are in the alkane, and the bench is your reagent. So you bring along for example, Cl2. I'll draw it this way, ClCl. Essentially what will happen is a H swaps around in its location with the Cl, and your products will end up being those same things, except you have the Cl swapped with one of the chlorines. So you get a haloalkane and a hydrogen halide as your products. And this requires UV light to proceed. Okay, so those are all of your hydrocarbon reactions. Let's move along to your alcohol reactions. So alcohol reactions, we have not as many, to be honest, but we have, first of all, combustion. How to define combustion? What is combustion? Yes, burning in the presence of oxygen, generally speaking. And in organic chemistry, we're burning hydrocarbon to make CO2 and H2O, but only in one of the cases. We actually have 3 cases of combustion. We have complete combustion, which is where you're making CO2 and H2O. So most schools will teach this combustion, you make CO2 and H2O. That's like band 4 or 5 level. If you want to go band 6, you need to know the incomplete cases as well. So you need to know that if you don't have enough oxygen, your combustion will also make it can make carbon monoxide and water. Or if you have very limited oxygen, you can also make carbon solid and H2O. And this carbon solid is what we call soot. It's a black powder, which you would see on the inside of like a chimney or in the mines. That is soot. Okay. Adding on to that, we also know about the substitution of alcohol. So you can go from a alcohol to a haloalkane from the substitution with HX, or you can go from haloalkane back to alcohol using substitution with heat and NaOH or KOH. The most important alcohol reactions are your oxidations. So oxidation refers to a reaction where you have if you oxidize something, it is where that substance will lose its electrons. There are 3 cases of oxidation with alcohol, and this is why it's important to understand what primary, secondary, and tertiary alcohols are. They will each undergo a different type of oxidation. A primary alcohol will undergo oxidation to aldehyde and H2O, and that will undergo, again, if you have more excess oxidizing agent, to go to carb acid. If you have a secondary alcohol, which means that there's 2 carbons attached to the carbon attached to the hydroxyl, you will go and form a ketone as well as water. So keep in mind that for the first oxidations of primary and secondary alcohol, you will also make a water because there are 2 hydrogens being dragged out of the alcohol molecule. The final case is for a tertiary alcohol. You have no reaction when an oxidizing reagent is present. Okay, then you also have fermentation. Fermentation is the production of ethanol and CO2 from glucose being fermented. And the reaction conditions are, you need anaerobic conditions. Otherwise, you have the ethanol turning into carboxylic acid from oxidation, and also you won't have the anaerobic environment you need for the yeast to work. You also need zymase, which is originating from yeast, and this is an alcohol-resistant enzyme which speeds up the process of fermentation, which usually takes anywhere from 3 to 5 days. 37 degrees Celsius. This is the optimal temperature of fermentation. Why is it 37 degrees Celsius? Why do we pick 37 degrees Celsius? There's 2 reasons why. Why is 37 degrees Celsius the optimum temperature fermentation? Enzymes denature past 37. It's more like 40, because if it was 37, we're doing it at 37. We're going to be denaturing on an enzyme. So we want to be sitting just underneath the enzyme's denaturing temperature. But we want to be as high as possible as well, so that we can maximize rate of reaction through our collision theory. How does a higher temperature increase rate of reaction through collision theory? Particles are more K, so what? Collide faster against each other. So we're getting there. Still need more. They collide faster. More percentage. I like that. Cheryl, that's good. More percentage are overactivation energy. And there's one other factor. So when you have a high temperature, you have a higher number of collisions. High number of collisions because particles will be colliding more frequently. There'll be more collisions per second. And on top of that, because of that faster movement, you'll also have a higher percent success rate, as Cheryl's talking about, because the percentage of particles overactivation energy is higher. So when any 2 particles collide, the chance of it being successful is actually higher if you have higher temperature and higher kinetic energy. Okay, so that's fermentation done as well. That's all the alcohol reactions as well. Leaving us just with acid and base reactions. You don't need to know how to make an amine, so this is actually not syllabus strictly, but you do need to know how to I'll cross out the arrow. You do need to know how to make an amide. This is important for our condensation polymers. So that is the reaction between amine and carboxylic acid using DCC and heat and reflux will make you an amide. And finally, to make an ester, you react carb acid with alcohol under with concentrated H2SO4 and reflux. Why do we need concentrated H2SO4? What does it do? What does concentrated H2SO4 do? There are two important reasons why we need it. Two mechanisms. Catalyst dehydration. Yes. So the catalyst part provides a alternate pathway with lower activation energy. Do not say that a catalyst decreases activation energy. That's not true. It provides an alternate pathway with lower activation energy. Then it also acts as a dehydrating agent because H2SO4 reacts with water, acting as a Bronsted-Lowry acid. It'll go and make HSO4 minus plus H3O plus, turning water into H3O plus, and hence taking H2O out of the system. Because esterification is a reversible reaction, or an equilibrium system which is reversible, you can shift the equilibrium right to increase your yield of ester, and that's why we use it as a dehydrating agent. So it's the same thing as the dehydrating agent in alcohols as well, because that's also a reversible reaction all the way back up here. And then the second thing, reflux. What is reflux? Why do we use it? Two reasons once again. Why do we use reflux in esterification? Good. Great. So I guess there's three reasons really, if you want to be comprehensive. First reason is it prevents loss of reactants, prevents loss of reactants and products, And as we say, it condenses things back down. As things turn to gas, the condenser in the reflux brings them back down as liquid. So that's your first one, prevents loss of reactant products. Secondly, it allows you to heat at a higher temperature because it allows you leeway to go above the boiling point, boil things, and rely on the condenser bringing them back down. So you can actually increase your rate of reaction by heating under reflux as well. And the third reason is a safety reason. Because the top of the reflux is open, it allows for pressure to be dispersed and you don't have an explosion within your setup. So three important reasons to reflux. And that rounds out all of our reactions within this pathway in terms of what you need to know. Okay. So we'll jump down to alcohols. We know now what primary, secondary, tertiary alcohols are. In terms of the properties of alcohols, we expect these to be high boiling point, low boiling point. Where do we place them and why? Alcohols high or low boiling point, they should have a relatively high boiling point because they are polar. They can form H bonding. They have OH. So alcohols should have a relatively high boiling point. Can they dissolve in water? Can alcohols dissolve in water? Yes, they can because they are polar molecules. They can form H bonds with water so that equal energy exchange is possible. Good. Comparing with other hydrocarbons like an alkane, an alcohol should have a higher boiling point because it has H bonds and dispersion, H bonds and dipole on top of dispersion. As you increase the chain length, the boiling point will rise because you have more electrons and the same flow as I mentioned before. But then there's an interesting trend between alcohols and alkanes. Chains will converge as you increase the number of atoms. And this is because of that reason we were talking about before. As you increase the chain length in a polar molecule, the influence of the polar portion becomes less. So what's actually happening is the initial amount of H bonding that you had, H bond and dipole, was accounting for this whole difference before. You can see that the difference at the end is decreased. And that's the only difference between these, because you're increasing the molar mass by the same for each of these. You're adding a CH2 on every single time. So what's happening is you increase the chain length of alcohols, the ability to form H bonding and dipole decreases because the influence of the polar part of the chain is less. And that means that your boiling point will still rise, but at a slower rate compared to an alkane. And you get this convergence of lines. All right. We've talked about this. We've talked about this. Let's keep moving. We've talked about all these alcohol reactions. We're done. We're done. We're done. Just touching on oxidation, just keep in mind that your oxidizing agents have distinct colors. So dichromate and permanganate are the ones you'll see by far most commonly. Dichromate starts orange and ends up green. If you do use it as an oxidizing agent, it becomes reduced. Whenever you oxidize something, something else has become reduced. So dichromate, being an oxidizing agent, it oxidizes other things. Therefore, the oxidizing agent becomes reduced because something has to gain the electrons that the oxidized substance lost. Sumya, I would say yes. I would say it's actually really important because if you don't know the colors in a question where they tell you, this, for example, this alcohol was placed in a dichromate oxidizing agent and it showed a green color, you would be expected to know that that is a primary or secondary alcohol that you've placed in because you've had a color change to the green color. And they might not even say that it's changed color. They say it just ends up as green. So what? You have to tell us that it is a primary or secondary because it's reacted. And permanganate would be purple and going to colorless if it oxidizes something. Okay. So then just the typical question they can give you, this is sort of veering onto mod 8. Butanol, propan-2-ol, 2-methylpropan-2-ol. These can each be reacted with an oxidizing agent. Say you do permanganate. What color should you expect for 2-methylpropan-2-ol? None, because it wouldn't react. Oh, wait, hang on. Is it none? Permanganate. Permanganate shows. Oh, yes, I think you're right. No, it wouldn't be because permanganate starts purple and ends up colorless if you oxidize something. But looking at 2-methylpropan-2-ol, 2-methylpropan-2-ol, this is a tertiary alcohol. A tertiary alcohol. And because permanganate in its oxidizing agent form is orange, sorry, not orange, purple. Only when it oxidizes something, it will turn to colorless. If you add in this oxidizing agent to a tertiary alcohol and nothing happens, it will just stay purple. Correct, it will stay purple in this case. But what if you added it to butan-1-ol or propan-2-ol? What would happen? What color would you see if you added to butan-1-ol and propan-2-ol? Colorless. It would be colorless if you gave it enough time. And I guess time taken for this reaction, let's not worry about it too much for now. Mod 8. So we just say that it will become colorless in the end for these two. Good. So you should be able to separate out primary and secondary alcohols from tertiary alcohols from this test. Enthalpy of combustion. Similar to what we talked about yesterday on enthalpy of neutralization, you need to know your two equations inside out. Obviously, combustion is a very exothermic process. Mean is a delta H, which is negative. Negative. You should be able to write out equations for combustion using your reactants and products. You should know it's going to be reacting with oxygen, making either CO2 and water in the complete case, CO and H2O in the incomplete if it tells you carbon monoxide, and soot and water if it tells you that. For the incomplete cases, they will tell you, they'll say you're making no carbon monoxide and you're making this black powdery substance, so soot, or they'll tell you you're making carbon monoxide only. It will only be one of the two in an equation unless they tell you otherwise, or they give you the equation to balance. Okay. Q equals M cap, delta H equals negative Q on N. Hopefully this is fresh from yesterday. M refers to the mass of what? Substance being heated, and N refers to what? Fuel burnt, reactant used. Good. Okay. Point of matching units again, always match your units. This is what your spirit burn and prack looks like. You'll burn some alcohol, measure the mass change, find out based on that how many moles of fuel you burnt. And from the temperature change you had, you can figure out how much heat was released per unit of fuel burnt. Hopefully you've all done this prack as well. So your typical question will give you initial burner mass, final burner mass. They won't usually give you the mass of alcohol burnt. You have to calculate that yourself. They'll give you the mass of water, or they'll give you the volume of water. So it's important to remember 1 mil of water is equal to 1 gram. You have delta T from the initial to the final. And oftentimes they can give you a graph of temperature change, which looks something like this. Say that this is 50, say this is 40, and say that you didn't start at 0. Or say that this is 20 at the bottom of the graph. Just say, for example, and this is like 45. What's the change in temperature? Where do you take your point from? Where this is temperature in degrees Celsius, and this is time. This goes to 45, this goes to 50. What's your change in temperature that you take? Not 5. What's your change in temperature? You're starting your experiment point at time 0, which is when you start heating it. This is showing a graph of how temperature increases over time. You eventually switch off your spirit burner. You might cool off a little bit. We don't want to take 25 either. The correct interval to take is actually 20 to 50. You want to take your maximum temperature recorded because that tells you the maximum amount of heat you released. And you should have, if you were to, in most graphs, you wouldn't get such a big decline. Usually you would hit your maximum, you would turn off your spirit burner at say this point, and your graph should end here at the maximum. It might dwindle a little bit, go down by a bit, and you stop there, potentially. You shouldn't have this big drop off at the end, but if you do, they're trying to trick you because this loss of temperature at the end is accounting for heat loss. And if you took this interval, you would be accounting for less of an increase in heat than actually happened. So you always want to take your biggest interval from starting temperature to end temperature in a change in temperature calculation for this prack. Okay. We've done this as well, making alcohols, fermentation, some of the reactions summarized, some pathway questions. Won't go through these. Biofuels, what you need to prepare is a response that compares biofuels against fossil fuels, as well as a response that compares bioethanol against biodiesel or biogas. I hate biogas, so just do bioethanol and biodiesel. It's oftentimes easier. I guess important things to discuss on biofuels. The carbon neutrality of a biofuel technically is it is technically carbon neutral if you're just talking about the substance on its own, but if you include the production process, overall, it is not carbon neutral because you have to use, for example, tractors to farm your grain, and that would take that would release more CO2 in the atmosphere than just what is going into that biofuel. So keep that in mind. It is carbon neutral, but not in practice. But yeah, the most important points are there. Some more notes. Won't go through biofuels too much. Organic acids and bases, we have aldehydes, ketones. We've already been through the alcohols. So we're just adding on aldehydes, ketones, amines, amides, carboxylic acids. Tell me about the intermolecular forces in aldehydes and ketones. What intermolecular forces do they form with themselves? Good. Dispersion dipole, dipole. Should they have higher or lower boiling point than alcohols? Good. Tell me about amines and amides. What intermolecular forces can they form between themselves? H bonding. And what bond allows for them to form H bonding? N. N to what? N to H. So they have N to H, and the H bonds will form between N to H and either lone pairs on the oxygen, you can form it like that, or you can form N to H going to a lone pair on another nitrogen. So those are both different H bond possibilities. Carboxylic acids, what intermolecular forces? H bonds. And they form H bonds between their what bonds? O to H. Good. So then amines and amides, carboxylic acids, they have a higher or lower boiling point than aldehydes and ketones. Good. Higher. Are they soluble in water? Definitely. They can form lots of H bonds. What about aldehydes and ketones? Are aldehydes and ketones able to dissolve in water? Ooh, contentious. No. Why no? Why no? Even at short chain length, can we dissolve aldehyde and ketone in water? Partially with short chain, yes. What intermolecular forces do aldehydes and ketones form with water? Dipole, dipole. Anything else? H bond. Controversial, but I like it. So aldehydes and ketones cannot form H bonds with themselves. We've said this before. They form dipole, dipole, and they form dispersion. Because as you can see on a aldehyde, for example, there is no O to H within it. There is no OH, NH, or FH bond. But it will still have this negative dipole on the oxygen because of its asymmetry. And when a water comes along with its negative dipole and positive dipoles, water's positive dipole on its OH can form a H bond with methanol, which means that short chain aldehydes and ketones are actually still soluble to some extent. They can form H bonds with water, which is what a lot of people get mixed up, because just because something can't form H bonds with itself doesn't necessarily mean it can't form H bonds with water. So just have that clear in your mind. Okay, same for ketones. In terms of boiling point, melting point, as we said, should be higher than alkanes, lower than things that can form H bonds, should be somewhat soluble. And you can see here for aldehydes, in fact, it is soluble until butanol, until it starts to become slightly soluble and then insoluble. Okay, amines, amides. We said before, we've named these at the start, so we know how to name them. Physical properties, there should be high melting point, boiling point, because they can form H bonds. We are going to run out of battery, so let me charge my iPad. Okay. They should be soluble. They should have high melting point, boiling point. But It depends if they're primary, secondary, or tertiary. How would a tertiary amine be different to primary and secondary amine in terms of intermolecular force? How would a tertiary amine be different? What intermolecular forces can a tertiary amine form? That's what you think. Lots of H bonding, but no. Forms no H bonding. Primary amines, where you have NH, H, primary amines form lots of H bonding. Plenty of H bonding. In fact, well, hydrogen networks. Is this more amides? I'm wondering, Zion, because I don't think amines form hydrogen networks. They form only one H bond per molecule. So amines don't form networks because they only have one lone pair, which limits how many H bonds they can form. And this would form, for example, a H bond with another H on another amine like this, right? Now, what happens if you make it a secondary amine? If you make it a secondary amine, you're replacing one of the hydrogens on each of these with a carbon, so make it another R. You can still form H bonds because you still have an NH on each. You have an NH, you have an NH, we're still happy. But if you go to a tertiary amine, now we're in trouble because we get rid of this last H. We have no more NHs. Does that make sense for everyone? You cannot form H bonds in a tertiary amine. And this is one of their favorite trick questions in the multiple choice. They'll throw in a tertiary amine or tertiary amide and ask you, can it form H bonds? Yes, I can explain it again. You can only form H bonds when you have N to H. When you make a tertiary amine, all of the NH bonds are replaced with N to C bonds because that's the definition of a tertiary amine, an amine where the nitrogen has 3 carbons bonded to it. If there are no more NH bonds, this amine can no longer form H bonds. And this is what we have here. This interaction is no longer possible. These molecules would only be able to interact now with dipole-dipole and dispersion. So, should tertiary amines have a higher or lower boiling point than primary or secondary amines? Higher or lower? Lower, because they can't form H bonds. Done. However, all these amines can still dissolve to some extent in water at short chain length because they still have that lone pair. So even tertiary amines can still form H bonds with water. So H bonding with water is different to H bonding with a molecule of its own kind. They're different relationships. And then amides form tons of H bonds. They can form 2 H bonds per molecule. And once again, if you end up with a tertiary amide, can you form H bonds in a tertiary amide? You cannot. Because if you replaced all of these H's with carbons, N to C, N to C, you can see that each and every single one of these bonds originating from one of those H's, this would be to a H, this would be to a H, this would be to a H. But if these are all changed to carbons, none of these H bonds are possible anymore. So for a tertiary amide, you cannot have H bonding either. And for a secondary amide, the H bonding capability decreases by 1 H bond per molecule. Yes. So they're still soluble for tertiary amides at short chain length because of the presence of lone pairs on the oxygen, which can take on a H each, and they also have a lone pair on the nitrogen, which can take on a H as well. So they can still definitely dissolve in tertiary amides, same as tertiary amines. Good. Carb acids. Physical properties are unique. They form what we call a dimer. How does dimer increase intermolecular force? Good. More dispersion force. Do not say, I'm okay. There's two trains of thought with dimers. I'm very much of the dispersion force train of thought. Some people say it strengthens H bonding. I don't really agree. But whatever your school tells you, that's what you go with. My understanding is that a dimer effectively is doubling the number of electrons in a functional unit. So when you have two carb acids that form a dimer together, it is two H bonds forming an interlocking structure. And what's essentially happening is the molecules that usually interact at an arm's length are being compressed into a smaller space, which means that the electrons are now gathered in a smaller space, double the electrons effectively in the same space. And that will mean that the dispersion force of this whole dimer unit is greater because you have a greater potential to form temporary dipoles from the larger number of electrons. So when you form dimers, you are increasing dispersion force. You're not affecting H bonding or dipole-dipole from the way I have always explained it and been paid marks. Okay. So then also carb acids soluble in water, but they don't form dimers when they go into water. They just dissolve. So you need to be able to differentiate amides from carb acids, from alcohols from amines. They all sit above everything else. You don't really have to separate anything from the middle column. So ketones, aldehydes, esters, haloalkanes, there's too much variation, too many finicky things for the HSC. So you're not expected to really separate those middle four if they're the same molar mass. But you are expected to separate the red from the orange from the green. That is like your bread and butter question. The harder questions will get to explain separating the red hydrogen bond forming molecules from each other. So there's three rules which help you to define which one will be highest, then next highest, and then going down. The more H bonds you can form per molecule, the higher melting point or boiling point, which is why amides sit at the top. They can form two H bonds per molecule. That's the way you justify it. Draw your diagram. The more polar the bond that's forming H bond is, the higher the melting point, boiling point. So if you have an FH forming H bonds compared to an OH, compared to an NH, these are different degrees of polarity because FH is more polar than OH, which is more polar than NH. So that is why amines that have NH have a lower melting point, boiling point compared to alcohols because they are less polar. The pole will be less and the attraction will be less, requiring less energy to break. And lastly, can you form dimers or not? This will increase dispersion force, and this is how you justify carb acids are greater in boiling point compared to alcohols. Okay. And these are the diagrams I would draw for each of them. So whenever you discuss these in a question, you need to justify the amount of H bonds they can form, or if they form a dimer, you draw this diagram to justify it. The markers love it. Doesn't go awry. Whenever you can draw a diagram, just chuck it in. Okay, organic acid and base. Big takeaway is carb acids are weak acids, acting as Bronson-Lowry acid, can make hydronium in water. Helps us to understand what citric acid is, we said yesterday. Citric acid is 3 carboxyls, which help us to understand why citric acid is triprotic, and ethanoic acid only has 1 carboxyl, so that's why it's monoprotic. We don't really need to worry about the strength. Bases that are organic, it's pretty much just amines. So an amine is a weak base, acts in the same way as an ammonia, and you have effectively the movement of electron pairs. Don't need to worry too much about it. If you want to read more into it, you can, but understand that amines are weak base. And therefore, the big takeaway from this whole inquiry question is that amines are weakly basic, carb acids are weakly acidic, and everything else sort of lies in the middle. Zion asks, how important would it be to know the inductive effect for organic acid and bases? So I've never seen it assessed explicitly. That being said, I haven't seen every single school's paper in existence. I'd say it's a low yield thing. If you're going for like high band 6 and you really want the understanding, sure, learn it. But like yield wise, it's not high yield. That's my simple answer. I've included in my notes because I think it's interesting, helps you understand strength of organic acid and base, and it's cool, but I wouldn't say it's highly relevant. Okay, we've talked about these reactions as well. And we're on to the final three topics. We have esterification, we have soaps, and we have polymers. And we're going to do it in 17 minutes. So esterification is the process of making esters, where you have the reaction of alcohol with carboxylic acid, and you're making yourself an ester, which is an alkyl alkanoid. So coming back to that idea of naming esters, the alkyl part is your alcohol, and your alkanoid part is your carb acid. So here, the ethyl is your alcohol, and your O8 is the part that has more O. That's how I always remember it, with the carboxylic acid there. Okay. Esters, they have distinct fragrances, so we know them to smell like pretty garbage in our labs. They're really bad, the ones we make in our labs, but they're meant to smell okay. Melting point, boiling point, they're like moderately high. What intermolecular forces can an ester form? What intermolecular forces an ester form with itself? Can it form H bonding? Not with itself, but it can with water. So it has dipole-dipole and dispersion with itself. With water, it can form the lot, but H bonding most importantly. Solubility-wise, that means it's sparingly soluble because of this centralized double bond O. It's not very soluble, only at very short chain lengths, and even then it's only sparingly soluble. The process of esterification, as we said, is the reaction of an alcohol with an alkanoic acid to make alkyl alkanoid your ester, as well as water. Do not forget that you make water in your esterification. Very common mistake. The reactions we said before, the conditions, where concentrated H2SO4 acts as a catalyst and it acts as a dehydrating agent. The reflux acts to increase rate of reaction, increase your yield, and also for safety purposes. So those are your reaction conditions and your reasons why. Understanding that when you react, it is the OH from the carboxylic acid and the H from the alcohol, which will spit out as your water in the end. And then the remnant oxygen on the hydroxyl from the alcohol attaches onto the carboxylic acid and forms your ester. Okay, so those are the reasons, benefits, safety considerations. Do not seal the top of your esterification process. If you seal the top, you're fixing the volume of your condenser or your flask. And that means as you heat up, you are increasing, you're fixing the volume and you keep volume constant. So V1 is also V1 here. You can effectively cancel this out and you're comparing pressure against temperature. This is if you seal the top. So when you increase temperature now as you heat, the only way to keep this expression true, so you're going from T1, to a larger T2, the only way to keep P1 on T1 equal to P2 on T2 is if pressure rises as well. And obviously, if a pressure rises within your flask, there'll be a large outward force against the walls, leading to an explosion as the pressure builds. So you don't want to seal your apparatus for that reason. You also do not want to use a Bunsen burner. I know some schools are really lax on this, but if you have alcohol from your setup and it turns to fumes and escapes, your reflux isn't perfect, that can combust and that can be dangerous as well. So you want to use a hot water bath or electrical heating plate or both. Boiling chips go at the bottom of your esterification process. They help to increase the surface area over which you heat, and that means you get a smoother boil, which prevents superheating, which leads to a phenomenon called bumping, where you have explosive ejection of fumes and you lose product as well as have, carboxylic acid fumes. It's not great. And finally, you always want to wear PPE, clean your spills. How do you clean a spill from an ester? Ester production, what are the things you need to clean if you spill your esterification contents? Sorry to hear, Soumya. Yes, the acid, how do you clean it? How do you clean it? How do you clean an acid base spill? We talked about this yesterday in mod 6. With a base, sure, but Na2HCO3 would be Correct. Something like sodium bicarbonate is really good. Why? It's amphiprotic, so you can neutralize both acid and base spills. You have it handy. It can be stored very easily. It's a solid. You can just sprinkle it over, and it's also a weak base, weak acid, so it won't overkill the effect. Okay, and then lastly, when you're isolating your esters, once you've made them, you need to be able to use a separating funnel. And the steps are adding distilled water so that you dissolve into an aqueous layer at the bottom. This aqueous layer will contain your carb, acid, and alcohol, as well as H2SO4, if there's any left over. The ester layer sits on top. You have to note this in your responses. You will lose marks if you don't say that your ester is on top, and it's because your ester is less dense. So it will sit on top as an organic layer. And that's because it's insoluble, does not dissolve in the water. And so this is what happens in your separating funnel. Once you place it in, you've done this all in an external beaker, and you place it in and mix up your separating funnel. You have this. You can also add in a step, and this is ideal that if you do add it in, where you add NaHCO3 or Na2CO3, which are weak bases, to your ester, like your whole reaction mixture, because it will react off any of the acid, this carb acid and the H2SO4 both will get reacted, making soluble salts, which will sit in the aqueous layer, as well as H2O, just makes more in your aqueous layer, and CO2, which buggers off. So it's taking some of that carb acid out for you and making really soluble substances that will just sit in your aqueous layer. Then, once you hit step 3, you can go and use your separating funnel, let off the lower layer of the aqueous part, which will sit in a conical flask, and in your separating funnel, you're left with just your ester. You can do this process several times over to increase the purity of your substance, adding water back to dissolve any remnant alcohol left over mostly. And you can do it a few times over to make sure your purity is as high as possible. The other way you can do this is through distillation, although this can be a bit more problematic if the boiling points are within a narrow range. So you have to be always sure that you know the ranges of the boiling points are quite distinct. Then you can use your purification method as distillation. But oftentimes it's going to be separating funnel is the best. And you can use distillation like a secondary purification. All right. This is what your setup would look like. Be able to draw it in with a ruler and pencil. Soaps and detergents. Okay, so soaps and detergents, you should know that soap is a carboxylate head with a hydrocarbon tail. The carboxylate head is polar, and the hydrocarbon tail is non-polar. This means that the head will dissolve in polar solvents. The tail will dissolve in non-polar solvents, like dissolving like, because of the equal exchange of energy. So what does that mean in terms of what we're doing with soap? Basically, it will affect how our soap acts in the action of cleaning non-polar substances such as grease, fat, oil. This first part doesn't really get talked about too much. It's a bit on the enrichment side, how soap goes into water and it will make a surfactant by splitting up water molecules on the surface and decreasing their interactions with each other. It means that water has less surface tension and kind of seeps into gaps more easily. But what you must know is the cleaning mechanism of soap. So there's 4 phases that I always talk about. There's the bridging, or there's the formation of a bridge, formation of use of agitation, the micelle formation, and the emulsion. And then I guess rinsing as well, but that ties into the emulsion. So there's 4 steps you must mention to get full marks in a soap question: bridge, agitation, micelle, emulsion, rinsing, BAMER, whatever you want to remember it as. But you start off by talking about how soap will form a bridge between water and the grease. The polar heads dissolve into the water and the tails dissolve into the grease, because the heads will be able to form what forces with water. What can the carboxylate head form with water? What intermolecular forces does the head form with water? H bonds, but what else? So this is your H bond, ion dipole as well. This is your H bond, and this is a ion dipole, because the O minus on the carboxylate head is a full charge. It is an ion. And the dipole on water is able to form, therefore, an ion dipole with it. So you have two significant intermolecular forces you must mention when you talk about the carboxylate head dissolving in water. You talk about the H bond forming and the ion dipole forming. On the other end of things, the non-polar tail dissolves into the soap, and that will form dispersion force with the soap. Because it's non-polar, the grease is non-polar, you'll have an equal exchange of energy, dispersion force forms. And so you have a bridging mechanism. You'll draw a diagram like this, and you move on to agitation. You must talk about agitation because if you think about it, if you douse a plate in grease, you dip it into soapy water, and you pull it back out, it's still going to be greasy. You have to be able to rub, apply a mechanical action, and start to get under the edges of the grease for the soap to start surrounding the molecule. So the soap is getting underneath, surrounding, and it ends up picking up the grease and forming what we call a micelle. So oftentimes I'll skip this step in my explanations in an exam, and I'll go straight to the complete micelle, where you have soap forming around a small lump of grease, completely enveloping it within it, and the grease is held in the non-polar portion with the tails facing inwards, whereas the polar heads face outwards towards the water dissolved. So what's essentially happening is you have this non-polar portion being shielded in a core. This whole inside bit is all non-polar, but because the heads are polar and dissolved, this whole lump of grease is now floating around in water, which is never supposed to happen because it's meant to be immiscible. This is the premise of an emulsion forming. That is what an emulsion is. An emulsion is where you have two normally immiscible liquids that are made to mix through the action of an emulsifier, and that is what soap is. Finally, once you form this emulsion, the micelles all have negative charges because the carboxylate heads are all negatively charged. How will the micelles interact with each other? If a micelle comes close to the other, how will it interact? Attract or repel? Negative to negative. Repel. They repel. And so once you form these micelles, they will cease to reform and they will stay individually in their own space in the water, waiting for you to rinse away your emulsion and hence get rid of all of your grease. That's the way it works. And the important steps, I shouldn't have put emulsion again here, would be as follows. Soap forms scum with hard water. Hard water is calcium and magnesium, water that contains those ions, and it forms rings around like your bathtubs or sinks, and that reduces the efficacy of soap. So detergents get around that. Detergents have increased efficacy in hard water, and they're synthetic synthetic compounds which mimic soap. These can come in anionic, cationic, or non-ionic forms, and they look something like this, where you have carboxylate, sulfate, trimethylammonium, or polyethylene glycol heads. They all interact, they all have the same mechanism as soap in the way it cleans. Just keeping in mind that for the anionic detergent, you still form soluble complexes with magnesium and calcium, so there's reduced efficacy in hard water still. And trimethylammonium, you have a positive charge because it's cationic. I guess you just have to acknowledge that when you form the ion dipole, it's with the oxygen instead of the hydrogen. And then for non-ionic detergents, you don't have any charge, so all you form is H bonding. There is no ion dipole. Okay, and obviously you can talk a lot more on the soaps, anionic detergents, and cationic and non-ionic detergents uses, but just to summarize them, for soap, personal hygiene, anionic detergent, using for more heavy duty purposes, dishwashing liquid, laundry detergent, glass cleaner. Cationic detergent has not like anti-static properties, so you can use it in your, or is that's kind of both cationic and non-ionic detergent. You can use it in your shampoo and your conditioner. And non-ionic detergent is really good for front-loading dishwashing machines because it doesn't make suds and you won't overflow your machine with suds coming out. Okay. We're not really expected to know saponification. That's more old syllabus, so I'm not going to cover it today. And finally, polymers. Polymers are massive chains of repeating units we like to call monomers. So polymer meaning many units. Addition polymers, you make use of a process we like to call, I guess, addition, where you have initiation, propagation, and termination, whereas condensation polymers are formed from condensation reactions, where you are either doing a esterification, making an ester linkage in the case of PET, or in the case of condensation reactions, you're doing a production of amide from the reaction of an amine with a carboxylic acid. Yes, carboxylic acid. And then in terms of what you need to know about the polymers, I probably will wrap up a bit earlier on the polymers just because there's still a lot to go. And if I go down the road, it'll take a long time. I'll keep it brief. For polymers, what you need to know is a vague understanding of how the mechanism works. If you understand, that's great, because that'll allow you to understand how it's actually made up. The structure makes more sense when you think in the order of thousands of monomers. So you need to know the mechanism, how it's made, the structure of it, of each of the syllabus prescribed polymers, the properties and the uses. And when you talk about properties and uses, you should be able to link each property to a use. So if you talk about how one is rigid, you explain why it's rigid. For example, it's, let's say, high density polyethylene is crystalline in nature. So it has a significant, it has a crystalline structure, which will have greater dispersion force, and it makes it a more rigid structure. This makes it useful for hard food packaging, like the hard plastic containers that you use. And this can be tied in with the example that PE for both low density and high density is unreactive and non-toxic because it only has stable carbon to carbon and carbon to hydrogen bonds. That makes it useful for food packaging. So you should be able to link each property with an explanation to its use. And you should have two at least for each polymer case. You have to cover HDP and LDP, as well as PVC. Polystyrene has expanded versus just like the normal polystyrene. And then PTFE is unique on its own. So there's actually 6 cases you need to cover. And for condensation polymers, you have nylon 6,6 as well as PET, understanding that nylon 6,6 is made from amide linkages, whereas PET is made from ester linkages. Again, they have their properties, link them to a use. The final thing I'll mention is that biodegradability of polymers, because people start to assess biopolymers by extending their reach of the syllabus. Addition polymers tend to be less biodegradable than condensation polymers because amide linkages and ester linkages occur in nature, whereas these carbon to carbon bonds are really stable and hard to break apart. So addition polymers, less biodegradable. Condensation polymers tend to be more biodegradable. So if we wanted to use something more sustainable going forward, we should try to use more condensation polymers than addition ones. That's all in module 7. Okay. So we're at the end. That's all. Hopefully, I didn't go too fast and you still got some value out of it. If you have any questions, I'd love to answer them at the end now. But other than that, we are starting class in just under 2 weeks now on the 1st of July. So if you are interested in getting a head start on this final trial period, and there's essentially a lot still to be gained in this last period of time. You've finished about 30% now of your internal mark. You still have your trial to go. So there's about 70% of your marks to go, 20% in trial and 50% from your HSC. There is no better time to accelerate and push on for that higher range mark, and we can help you do that in this last period. The way we'll do that is we'll cover all of Module 8 during the holiday in a quicker system. So you'll start week 1 of the holiday, finish in week 3, all of Mod 8 done. So when you step in the classroom next term in week 1, you've got all your content done. It's just a matter of doing questions from that point forward. We'll be running a trial exam in week 1 as well, which we write all of our own questions for, which is, tailored to what's going to be in your trials most likely. And if you have that experience from week 1, you've set a full trial and the time conditions 3 hours long, get it marked back to you. That accelerates your learning so much faster next term than just going back and doing content and doing some practice questions here and there. You need that exam experience. And from our experience, it really does help. So if that sounds like something you'd like to make use of, send us a message and we'll be happy to have a chat. But other than that, I'll stick around for some questions. And if you have to head off, enjoy your evening. Thanks for coming.